These means these are the equations can be constructed from like this here. Okay? Y is a function of x. Y is a function of x. Y is a dependent variable. X is an independent variable. Y is a dependent variable and x is an independent variable. Y is depends on only one variable. If it is y is depends on only one variable, from this we can construct the differential equations here, like d square y by dx square plus 2d dy by dx plus y is equal to 0. Similarly, dy by dx whole square plus 2y equal to 0, that type of things. Y is depends on x only. Y is depends on x. Then from this function, if you want to relate that functional relations with the help of the differential equations, you can get this type of equations here. This type of equation. These are all ODEs here. In the case of PDEs here, you can say that it contains more than one independent variable here. It contains more than one independent variable. Now U is depends on both x and y here. U is depends on both x and y here. X and y, or U is a function of x and t. X and t, that type of thing here. If it is more than one independent variable, these are all independent variable. This is a dependent variable. This is dependent variable here. Independent variable, dependent variable here. In that case, you can get what yeah, if you get derivative here, you have to use partial derivative because more than one independent variable. U is depends on more than one variable here. Therefore, in that case, you have to use partial derivatives. Partial derivatives here, as already you have seen in the third semester Laplace's equation here, dou square u by dou x square plus dou square u by dou y square equal to 0. Similarly, heat equations here, dou square u by dou x square equal to a into dou u by dou t. Heat, one-dimensional heat equation, that type of thing. These are the things are called a partial differential equation. Partial differential equation. Whether this kind of situation arises or not here in the real time, yes, definitely. Suppose the real time that type of situation, can you get that here? Yes, more application oriented problems are purely based on more than one variable here. More than one variable. Suppose this is your metal rod. Metal rod. This is it has a length L centimeter, a metal rod of L centimeter here. You are making heat from one end here. You are making heat from one end, the initial position x equal to 0, and we are heating up to 15 minutes or 10 minutes here, and then the metal bar get heated here. The metal bar get heated. Then temperature inside the metal bar we are going to measure by you are going to measure the temperature inside the metal bar here. That will be termed as a U. That will be termed as a U. So after heating 15 minutes, you are going to measure the temperature because you are heating at this point here. Therefore, it may get some higher temperature here. This end point may be somewhat of lower than this part here. Lower than this part here. That middle part have some other temperature. Therefore, now heat is depends on x, the distance, x equal to 0, the point value here, x equal to 0 to x equal to l. And moreover, initially you measured at after 50 minutes. Then after 30 minutes, if you measure here, the heat may vary. After 45 minutes, if you measure again, the heat may vary at different points here, different points here. Therefore, here now the temperature inside the metal bar U now is depends on both the distance, the point we are going to measure, and also the time that we are going to consider here, the time we are going to consider. Therefore, now here the temperature of the metal bar U is depends on both x and t, both x and t. Therefore, this will be a real time example where a variable is depends on both variable, one more than one variable, more than one variable. U is depends on x and t. U is depends on x and t. In that manner, we can get that. Therefore, if you from that relation, if you want to find a relationship with the help of the differential equations, you may get this type of equations here. This type of equations, those such equations are called partial differential equations here. Differential equations are differential equations that contain differential equations which contains more than one independent variable. More than one independent variable. More than one independent variable. Such differential equations are generally noted as partial differential equations. Partial differential. It is only one independent variable. Ordinary differential equations here. Yes, it is possible real time. Yes, it is possible. Variables depends on more than one. Is possible here. Or this will be a simple example for the how to get a partial differential equation. How to get a partial differential equation. This idea. Yes. Now some standard notations you are going to use in partial differential equations. Standard notations based on your textbook conditions here. We are going to use some standard notations in the partial differential equation here. Generally, the metal bar temperature or something you just now you have used the notation as u is a function of x comma y. U is a function of x comma y or x comma t function x comma t and so on here. And this is the idea now. So far we have considered that here. Now generally in the textbook notation we are going to follow z is a function of x comma y. Suppose z is a function of x comma y here. Z is a function of x comma y. I can use z, u or anything here, but in the standard level they are going to use the notation as a z. Z is a function of x comma y. Z is depends on more than one variable. Z is depends on both x and y. In that case, if you differentiate partially with respect to x, y, you can use some notations here. You can use some notations here. Then you can use dou z by dou x as a p notation, standard notation as a p. Similarly, dou z by dou y, dou z by dou y as a q, a standard notation q. Partially with respect to x means p, and partially with respect to y means q here. And then second derivative dou square z by dou x square as a r, and then similarly another second derivative dou square z by dou x dou y equal to q, sorry r not q, r s here, not q. This will be s. Then another second derivative dou square z by dou y square equal to t. T. Therefore, these are the standard notations some we can use in the throughout the concept here. Suppose p means that p represents dou z by dou x, first order derivative with respect to x. First order derivative with respect to y means q. Second order derivative with respect to x r. Second order derivative with both x and y means s. Second order derivative with respect to y means t. With respect to y means t. In that manner we can use it. Therefore, these are the standard notation we can follow. Yes, suppose you have p minus q is equal to 0 means it is a partial differential equation. It is a partial differential equation that represents here. Similarly, r minus s plus t equal to 0. Yes, it is also represent a partial differential equation. Partial differential equation here. With the help of these notations, with the help of these notations, we are going to identify these things. We are going to identify these things, right? For these standard notations, you have to remember P represent dou z by dou x, Q represent dou z by dou y here. Second orders are R, S, T. That type of form you can get that. Okay? That you have to remember always. Now, the differential equations based on the order and degree, based on the order and degree of the differential order and degree, we can classify the differential equations PDEs into many type here. Many type here. Therefore, we have one more definition, that order. Order means what here? Order is the order of the partial differential equation here, and the order of the highest order derivative. The highest order derivative present in the partial differential equation. Highest ordered derivative is called order of the partial differential equation. Order of the partial differential equation. And similarly, you have another one, degree. Degree of the partial differential equation. The power of the highest ordered derivative. The power of the highest ordered derivative. The power of the highest ordered derivative is called degree of the differential equation. Called degree of the partial differential equation. The same as the ODE, ordinary differential equation. It's both the ODE or PDE, the same definition only here. The highest ordered derivative present in the differential equation is called order of the differential equation. And the highest power of the highest order derivative is called degree of the differential equation. Okay? Degree of the differential equations. Based on this definition, suppose if you consider the differential equation like this here, dou square u by dou x square, dou square u by dou y square equal to 0, and then dou u by dou x whole square plus dou square u by dou t, dou square u by dou t square equal to u. Suppose another one is that dou square u by dou x square equal to a into dou u by dou t, a into dou u by dou t. In that case, what will be the order and the degree of the differential equations? What will be the order and degree of the differential? Highest order derivative here 2 dou square u, dou square u, dou square u. For both are 2 2 only here. Therefore, order is 2. What will be the power of the highest order derivative? This 1 only here. It is also power 1. So degree is 1 here. Both have the same order. The same order have a common power 1 only here. Therefore, degree 1. Can you give the answer for this one here? What will be the order and degree?
2 and 1.
Order degree 1.
2. The highest order, this is the highest order. This power is 1. Therefore, 2 and 1. What is the order and degree here?
2 and 1.
Again 2 1. 2 1. Highest order is this one, and 2, and power is 1 here. 2 1 here. Order and degree of the differential equation. So in that manner, we can say that here order and degree of the differential equation. Right. Suppose order is 1, such a differential equation always called as a linear partial differential equation. Suppose the equations have order 1, such a differential equations always called linear partial differential equations. Linear partial differential equations. Suppose that can be considered as a p square plus q square equal to 1, p minus q is equal to 0. Examples. Examples. Here dou z by dou x, dou z by dou y, dou z by dou x, dou z by dou y only here. But the degree, this is degree only, but order is always 1. Order is always 1 here. Such as px plus qy equal to x square, anything. These are all the order is 1. Order is always 1, but degree may be anything. But that such differential equations are called linear partial differential equations here. Linear partial differential equation. Suppose order is greater than 1, more than 1, order is greater than 1, order is greater than 1. Such differential equations are called higher order PDEs. Higher order PDEs. Such partial differential equations are called higher order PDEs. It may be order is more than 1. Order is more than 1. Such equations are called higher order PDEs. In that way, we classified. We have the classifications here. You see that here in the solution here, first order nonlinear PDE. First order nonlinear PDE. Yes, these are all the PDEs, different type of PDEs. We are going to see that up to Lagrange's linear equation. We have the different type of first order. First order means first order PDEs. First order. Generally, they are also called linear PDEs. Linear PDEs here. But non-linear in the sense means degree. Maybe something degree is higher. And here higher order PDEs. Higher order PDEs here. That will be more than 1 here. More than 1 here. For such type of thing, we can going to see that here. Higher order PDEs. Generally, instead of linear, first order PDEs. Instead of linear, you can say that it will be first order PDEs, partial differential equation, higher order PDEs. First order, higher order PDEs. first order and higher order PDEs here. First order we have many different types here. Similarly, higher order PDEs also we are going to see that. So in the throughout this chapter, we are going to see the solutions of first order PDEs here. Similarly, higher order PDEs here, higher order PDEs, and then applications part here, applications part that we are going to see that. Right. Now, at initial step, we are going to see the formation of PDEs. Formation of PDEs. This formation of PDEs can be done by eliminating arbitrary constants. You are going to form from the given relation. From the given relation, we are going to form the PDE by eliminating arbitrary constants. Arbitrary constants. And the second one is by eliminating arbitrary functions. By eliminating arbitrary functions. By eliminating arbitrary constants and by eliminating arbitrary functions here. Yeah, from relations, okay. In the initial step, we are going to see that formation of PD, eliminating arbitrary constant and eliminating arbitrary function here. For that purpose, formation of PD means from the given relation z x y, we are going to consider constructed PD. You are going to construct the PD by eliminating arbitrary constant, eliminating arbitrary function, eliminating arbitrary. For that purpose, just to differentiate partially with respect to x and so on, you can get it. If you take some simple problems based on this idea here, form the partial differential equation. Form the partial differential equation. Number one, z equal to from number one z equal to x square plus a into y square plus b, where a and b are arbitrary constants. Where a and b are arbitrary constants. Found the PDE, partial differential equation, from the given condition, from the given relation. Some relationship is given between z x y. Z is x y. From that, you are going to form a PDE by eliminating arbitrary constants without having a and b. A and b. The idea is very simple. First of all, you write what is the relation is given. What type of relation is given? Z equal to x square plus a into y square plus b. Z equal to x square plus a into y square plus b. Now differentiate to get partial differential equation. Differentiate equation number one partially with respect to a. Partially with respect to a. Then you can get dou z by dou x. Dou z by dou x left side. Partially, sorry, with respect to x, not a. Partially with respect to x. With respect to one variable here, x. What about here? Right side is 2x, 2x. Here there is no, you have to keep this one as it is. Product model, UV model. Differentiate this one 2x. Keep as it is here. Plus, now keep this one as it is here, x square plus a, and differentiate this one 0, 0, 0. Now this dou z by dou x can be notated by standard notation p. Therefore, you can get it as 2x into y square plus b. Y square plus b. This is the idea you can get that. After differentiating partially with respect to x. Similarly, differentiate again the same thing, partially with respect to x over, similarly partially with respect to y. Partially with respect to y. Partially with respect to y. What you can get here? Dou z by dou y equal to partially with respect to y means this is y only, this is here only y, therefore we have to get x square plus a into 2y. But dou z by dou y can be notated simply by q, and here x square plus a into 2y. X square plus a into 2y. What about idea we require here? We have to get partial differential equation. Partial differential equation means maybe in terms of PQ or partial derivatives here. Therefore, we need PQ, but no need of A and B. No need of A and B. Yes, we have to eliminate a and b means here x square plus a is separate one, but x square plus a is here. Yes, here is also x square plus a. Therefore, we can totally replace this x square plus a by q by 2y. So, like you totally replace y square plus b. Yes, here is also there. You can replace by p by 2x. You substitute here, you can get an equation. Equation. So, from 2 and 3, from 2, what you can get here, y square plus b is equal to p by 2x. Y square plus b is equal to p by 2x. Similarly, from 3, from 3, q by 2y equal to x square plus a. Q by 2y equal to x square plus a. Now substitute these two. Substitute these in equation number 1. Equation number 1. What you can get here, z equal to x square plus a into a square plus b. Z equal to x square plus a. X square plus a is equal to q by 2y into y square plus b. Y square plus b is equal to p by 2x. P by 2x. What you can get here, 4xyz equal to pq. Pq here. This is the required partial differential equation. Is the required partial differential equation. As PQ are partial derivatives here, and then here some relationship here. Relationship or you can write like this here: 4xyz. 4xyz equal to dou z by dou x, dou z by dou y. Dou z by dou y. In that manner can write. Okay, right. This is the idea of how to construct a partial differential equation from the given relation. Okay, from the given relation. From the given relation. Can you give the answer for idea is very simple. What about the relation is given? You write that differentiate partially with respect to x and partially with respect to y. Partially with respect to y. And then you have some relationship here. From that, can we eliminate this a and b? Is it possible or not? You check that here. Yes, it is possible. From that, you can get the directly you replace here. You can get some relationship. Okay. Can you give the answer for this one here? Second problem here. Is it equal to ax cube, where a and b are arbitrary constants? Where a and b are arbitrary constants. Can you give the answer for the partial differential equation? Partial differential. Is all of you try like a previous problem, differentiate partially with respect to a and partially with respect to x, partially with respect to y. Is that equal to ax cube plus by cube?
Three z equals to px plus qy.
Ah, 3z answer?
Three z equals to px plus qy.
Yes, px plus q. Yes, very good. Differentiate partially with respect to x squared, p is equal to 3x square. To a you can write here. Similarly, q is equal to so on here 3by square. 3by square. From that you can write b. Yeah. Substitute that you can get the answer. You can get the answer. Your solution will be like this. Required partial differential equation. Is all of you getting the same answers? Just to differentiate with respect to x, with respect to y, and you can get the value of a and b. You can get the answer. Okay, can get the answer. take one more problem here. Z equal to 1 by 2 of square root of x plus a plus square root of y plus a, square root of y plus a plus b. Here both are a only, a, and here is also a, and here b is separated one. Okay? B is separated one. What about here? We take it as equation number 1. Differentiate 1 partially with respect to x. Then what you can get here? P is equal to 1 by 2 of partially with respect to x means here you can get it as 1 by 2 x plus a minus 1 by 2, and 1 only here, 1 only is the square root of x plus a, square root of x plus a, and here 1 only here, and then this is purely y here, purely y, therefore that will be 0, and then this is constant b here, this is constant, therefore that will be 0 here, that will be 0. Therefore you can get this equation only, this equation only, square root of 1 by 2 nx power n minus 1, and differentiate one more time here. So you can get this relation only, this relation. So what you can get here, p is equal to 1 by 4, 1 by 4 of square root of x plus a. P is equal to 1 by 4 of square root of x plus a. Similarly, differentiate partially with respect to y. Similarly, differentiate 1 partially with respect to y. With respect to y, what you can get, left side is q, left side is q, and here is also the same thing here, 1 by 2, 1 by 2 can get here. So 1 by 2 nx power n minus 1, y plus a, y plus a, nx power n minus 1, and this is 1 only here, and plus b, that is also 0. Then what you can get here, q is equal to 1 by 4 of square root of y plus a, y plus a. This is third equation, third equation. But we have to eliminate both a and b, where a and b are arbitrary constants. Both a and b are arbitrary constants here. So we have to eliminate both a and b here. But here elimination, x plus a you are getting here. Square root of y plus a, that's also you are getting here. That's okay. Square root of y plus a also you can get here. But if you substitute here, but again b is again appears here. B again appears, but we have to know that b also here. Therefore, the only way is that from this equation, you have to get what is the value of a. From this equation, what is the value of a you have to get. So from this equation, what is the value of a you have to get. Then both are a, both represent a. Then you can equate both a here. Right. Now squaring, that is the only possible. That is the only possible. Squaring 2, 2 is what here? P is equal to 1 by 4 square root of x plus a. P square means what you can get here, 1 by 16 x plus a, x plus a. For from this what you can get here, x plus a is equal to x plus a is equal to 1 by 16 p square, 16 p square, 1 by 16 p square here. From this, what is the value of a, that is also you can write here. Therefore 1 by 16 p square minus x, minus x is the value of a. Similarly, squaring 3 also the same thing you can get here. Squaring 3, what you can get, q square is equal to 1 by 16 y plus a, y plus a. Therefore, y plus a equal to 1 by 16 square, a equal to 1 by 16 square minus y, minus y. This is also a. Now it is also a from this relation, from equation number 2. It is also a from equation number 3. Therefore, both represent a, the same arbitrary constant. Therefore, both are same. Therefore, what you can get here, therefore, we have 1 by 16 p square minus x, 1 by 16 p square minus x is equal to 1 by 16 q square minus y. So 1 by 16 p square minus 1 by 16 q square equal to x minus y, x minus y. 16 you can take it commonly here, 1 by p square 1 by q square equal to 16 into x minus y. Oh, this will be the required partial differential equation. This is the required partial differential equation. Is the required partial differential equation that you can get that. This is the way, because here again b appears here. B appears, therefore by substituting this we cannot get any idea properly. The only way is that we try to identify that arbitrary constant value here in the both the ways, and you can get the answer. You can get the answer.